So a few announcements. We have a new homework assignment that is posted. Thank you for those of you who finished last night's assignment and have that done. If you are getting behind on Chem 101, that is a quick way to start doing poorly in this class. So staying up on your homework will really help you to understand when you are in class, know what questions to ask, get better prepared for the exam. So make sure you are staying up on those. Use some time this weekend to catch up if you have not finished those homework assignments. So number 4 is due on Tuesday. That's going to cover formal charges. I'm also going to post another one that will be due the same day that covers some of the stuff that we're going over today and perhaps Monday. So you'll have a couple of things that are going to be due the same day, but I've broken them up so that you don't have to spend a whole long time doing just one thing. You can do them in pieces. You also have a quiz coming up. I know we just had a quiz. I don't have them graded yet. I should have them graded and posted by this afternoon and get them back on Monday. But you have a test on February 9th. And so I want to get another quiz in so you have the opportunity to see some of this newer material on a quiz before we get to the test. So quiz 1 week from today, test the following Wednesday. My intention was for the test to cover all of chapter 7 and 8. I don't think we're going to get to the end of chapter 8 by the time we get to the test. But we will get to some of the material in there. Let's see. I think that covers announcements. Questions? This slide, if you were still right. Okay, first thing I wanted to talk about was what we mean by bonds. And we're going to be discussing, as you saw on that other slide, inter and intramolecular forces. And in this chapter, we are interested in the intramolecular, what's going on inside the bonds or inside the molecules. And so we have here a boiling clear liquid. So that liquid might look like water, but our molecules show us differently. There's lots of clear liquids. And on the bottom, we see the molecules as they might be in the liquid phase. And so in the liquid phase, we have these attractions from one molecule to the other, represented by these dotted lines, okay? Now notice that when I go from the liquid to the gaseous phase, I haven't changed the molecules themselves. The one that's on the far right kind of looks shorter, but it's just turned on end. So we're looking at it down the end of the molecule. So the real difference between them is that they're farther apart, okay? So intermolecular forces would be the attractions or repulsions between molecules, between one molecule and the next molecule, between nearby molecules. And in this case, they happen to be the same molecule. They don't have to be. We will talk about intermolecular forces more when we get into chapter 10. So in this chapter, we're going to be focusing on what's going on inside of the molecule. So if you look at the top, there's a line pointed between the atoms there, and it says strong covalent bonding forces are within the molecules, okay? So the point of this is that holding the atom together, holding the molecule together as a molecule is a lot stronger than keeping one molecule next to the other molecule. Another important thing to remember is that if we have a phase change, like boiling water, or in this case, boiling, I think that's pentane, we don't actually break apart that molecule. Okay, so we didn't change this from a molecule with 5 carbons and 8 hydrogens to smaller molecules. When you boil water, you still have a hydrogen and an oxygen and 2 hydrogens, right? What's floating around in the air is not hydrogen gas. It's not, well, I mean, there's oxygen, but it didn't come from what you boiled, right? So, so when you boil something, when you have a phase change, the molecules don't change, okay? So that may seem obvious to you, or it may be something that it's like it never occurred to you to think about it. And so for those of you that it never occurred to think about it, I want you to remember that. All right. Oops. Oh, what happened there? I don't know. I think the slide got moved. Okay. All right. So inter versus intra, and I should really reverse this because I talked about intra on the left and inter on the right. But intra, like intramural sports, are inside of a school. One group of people from the school play another group of people from the same school. So it's inside. The bonding is intramolecular. And usually when we talk about this, we're talking about covalent bonding. Ionic bonding kind of fits on a borderline where it depends on whether you're thinking of the crystal as being like a molecule or whether you're saying, no, each ion is its own independent thing. And we'll see energy wise, it kind of fits that way too. But everything else between molecules is intermolecular forces. We're focusing on this left-hand side here. Covalent bonds are very strong, by and large. There are a few exceptions. And so that means it's very hard to break these bonds. So it's a lot easier to pull one water molecule away from another molecule than it is to break apart a molecule, water molecule. And since this is chemistry, we're worried about what chemical reactions are. Chemical reactions always involve breaking and forming bonds. Okay, so you probably somewhere along the way had a science teacher that talked about chemical changes versus physical changes, and they gave you some markers for how you could tell the difference between them. Things like, is it easily reversible, or does it have a color change? And those are generally good indicators, but there's always exceptions. In the case of breaking and forming bonds, this is absolutely true. Like, this is kind of our defining point of what a chemical reaction is. If we didn't break any bonds or form any bonds, we didn't do a chemical reaction. Okay. All right. And then just briefly, the intermolecular forces are relatively weak. So relative to the covalent bonds. And when we disrupt those intermolecular forces, IMF means intermolecular forces. When we disrupt those, we're not breaking them because they're not bonds, but when we disrupt them, it does not imply a chemical reaction. So just like we said on the previous slide, if we boil something, we're not breaking the bonds. Okay. All right, so we've seen this picture or similar pictures before, just sort of describing what a covalent bond is. So remember, in a covalent bond, we are sharing electrons. So on the left here, we have two atoms that are sort of overlapping, because remember, the outside part of the atom is where the electrons are. So they overlap in the sense that they are sharing that electron. The electrons in that bond are part of both of those atoms. So it overlaps. Because they're negative, they're attracted to both nuclei. Okay, the nuclei don't want to get close together, but they do want to be close to the electrons, and the electrons are attracted to both of the nuclei. So we've got sharing going on. We've seen the right-hand side before. So remember, what we're showing here is it's called the electron density. You can kind of think of it as, where am I likely to find that electron? And the most likely place to find an electron is close to the nucleus, because opposites attract. So that's why we got those two peaks that represents the electrons that are hanging out near the nuclei. Those are what we call core electrons. And the other electrons are a little bit further away, but the highest point for those further away electrons is between the two atoms. That's where they're being shared. Okay. We've seen this diagram before, slightly different, but still the same idea. Remember, this is called a potential well. So in chemistry, usually our graphs on the left-hand side, we're measuring energy, and usually it's potential energy. Okay, so energy is lowest when we're most stable and highest when we're least stable. So this is called a potential well because we've got sort of a dip down, creating a well of potential energy. On the bottom, we are measuring the distance between the two atoms, what's called the internuclear distance. So we're measuring that distance from one nucleus to the other. And over on the right-hand side, we've got those atoms so far apart that they cannot sense one another. Remember, atoms don't have eyes or ears, so they're blind. They can't see there's another atom. On the left-hand side, these atoms are practically on top of one another, and those nuclei are so close, they're pushing each other away. They do not like that. They are not happy. So it's really high. The potential energy is really high. The graph is really high there because that's a very unstable situation. The atoms don't want to be like that. And then at the bottom of this well, we have this sweet spot, and that sweet spot is the ideal distance between two atoms that are bonded together. So you can see at the bottom, there's a 74. In this particular case, I think we're looking at hydrogen. That would be the bond length of a hydrogen-hydrogen bond, okay? So the bottom of a potential well tells us left to right how long the bond is. And we talked about that before. What I want to look at are these yellow arrows. This is the energy associated with the bond. This is what we're going to focus on for this section. So we've got that zero line going across, and that zero line meets up with, asymptotically, to use a math word, with the energy when the atoms are completely separated. So that represents there is no attraction, no repulsion at all, okay? The difference between a bonded atom and no interaction at all is the energy of the bond. Now, since forming a bond is at the bottom of this well, it's more stable. In order to go down to the bottom of the well, we release energy, okay? So it is negative energy, released energy to form a bond between two atoms. To break that bond, just like breaking a stick, you have to use energy to break it. And so that is a positive energy. Now notice those two arrows are the same length. So it's the same amount of energy to form or to break. It's just one is positive, one is negative. Okay. All right, so here, here's your chart. And the main thing that I want you to get out of this is the concepts of relative lengths and energies and things like that. We're going to do some calculations. They will show up on your quiz and on your test, but they will be worth few points because it's not the most important thing that we're doing right now, okay? Most important is to recognize if I compare different bonds, can I tell which one's going to be longer? Can I tell which one's going to be weaker? That kind of thing. So the first thing I want you to do is look in the upper left-hand corner where we have hydrogen going down. And hydrogen is bonded first to hydrogen and then fluorine, chlorine, bromine, iodine. Okay, so each of the halogens. So since those are all in the same family and we're going down the periodic table as we go down that chart there, we know that we're getting bigger and bigger atoms, right? That makes sense? Okay. So let's look at the length of the bonds. What happens to the length of the bond as hydrogen is bonded to a heavier and heavier atom? It gets further away, and that shouldn't be too surprising. Bigger atom, of course, the length is going to be different. Okay, so one thing in chemistry makes sense. Yay. Let's look at the energy now. What happens to the energy as the bond gets longer? Yeah, so the hydrogen to the fluorine's a little bit off, but otherwise it gets smaller. As a general rule, the longer the bond, the weaker the energy, okay? And we can see it's not 100% true, but as a general rule, the longer the bond, the weaker the energy. Okay, so the next thing that I want you to notice is that the top part, we all have just one line, but at the bottom, it says multiple bonds. On the left-hand side, there are double bonds, and on the right-hand side, there are triple bonds. So that means that we're going to have a different length and different energy when we compare multiple versus single bonds. I want you to pay attention to the C double bond O that is in the lower left-hand corner. So most of the time when this happens, we call it a carbonyl. This is an organic functional group. And the carbonyl has a pretty consistent 745, right around 750 energy. But notice that if it's in the molecule carbon dioxide, it's 799. Okay. So when you do these calculations, one of the common mistakes is forgetting that, oh yeah, it's going to be different for carbon dioxide. And I'll show you an example of that in just a minute. For some reason with the dioxygen, they wrote O2 instead of showing the double bond. That's not significant on here. It's the same thing as if they put O double bond O. All right, so we look at the next thing. Relationship between bond order and length and strength. So on this chart, the length is listed first. So let's look at our first 3 carbon-oxygen bonds going from a single bond to a triple bond. What happens to the length of the bond as it gets to a higher order? It gets shorter. Yeah. So this is one of those concepts that I was saying, this is far more important than the calculations that we're doing. You need to understand that the higher the order of a bond, the shorter it's going to get. What happens to the energy? It goes up. So as I increase the order of any bond, the energy will always increase for higher orders. Okay. The amount that it increases is a little bit different, and we'll talk about that in just a minute. All right, so if we look at the carbon-carbon bonds, we should see the same trend. Going from the single bond to the triple bond, it gets shorter. But going from the single bond to the triple bond, we have a higher energy. And the same thing for the nitrogen-nitrogen bond, okay? So higher order bonds are shorter and stronger. So if you think of a bond like a spring, then a triple bond might be like a really tightly coiled spring. So it's a really strong, it's hard to, pull it apart, but it's also really short, okay? But if you have a long single bond, it's kind of like a slinky where it's all floppy and stuff. All right. The next thing that I want to look at is comparing. This one's a little bit odd to look at, but this is looking at the value added. So how much additional energy do I get by increasing the bond order? Most of the time, what we're going to see is a decreasing amount of added energy. So we're still getting a higher energy bond, but how much more energy is a little bit less. So what do I mean by that? Let's look at the carbon-carbon bonds. Going from the carbon-carbon single bond to the carbon-carbon double bond, if I were to double the energy, 350 doubled is about 700, right? And so we're just shy of 350. We would expect that if we had an identical amount of energy for the second part of the bond, that the total bond energy would be around 700, but it's not. So the first part of the bond, the single bond, is 347, but we didn't add another 347 to get to the double bond. We added a little bit less than that. That's what I mean by the value added, okay? So it's still a higher energy bond, but the additional energy is not quite as much as the original energy. Then if we go to the triple bond, going from the 614 to the 839, we have just a little over 200 being added there, okay? So again, not as much energy being added for that third layer of the triple bond as we had for the single bond or the amount added for the double bond. Is that making sense? Do you get what I'm trying to get at there? Okay. So if we think about this, this is kind of like saying the first part was a 3, then we added 2, then we added 1. So we're adding a little bit less each time, okay? And most bonds work that way. Nitrogen does not. So I want to point out the exception on this. And then when we get to chapter 10, we'll talk about why it's a little bit different. I'm sorry, chapter 8, we'll talk about why it's a little different. So if you look at the nitrogen-nitrogen single bond and compare it to the carbon-carbon single bond or the carbon-oxygen single bond, first look at the length. Are they pretty similar in length? Each of those single bonds? We got a 143, 154 is a little bit longer, and a 146. So not too far off of one another. There's a little bit longer bond for the carbon-carbon. All right, now let's look at the energies. Carbon-oxygen, 358, carbon-carbon, 347. Those are not too far from each other. Nitrogen-nitrogen, 160. That's a lot less. That's less than half of the others. Okay, so a nitrogen-nitrogen single bond is very weak. Okay, we very rarely see stable molecules that have a single bond between two nitrogens. So anybody remember what's the bond order of nitrogen in the air? All right, so you could do the dot structure and draw it out, but for the sake of time, I'll just tell you it's a triple bond. Yeah. So that's a very strong bond. All right, now what happens with our value added with the nitrogen? So if I doubled 160, the energy of the single bond, if I added the same amount, I would be at 320, but instead I'm at 418. So adding that second layer actually added more energy than the original bond was. Okay, so this is our counterexample, the exception that proves the rule. And then going to our third layer, we add even more. So this would be like 1 plus 2 plus 3. Each time we're adding more than we added the last time. Okay, so nitrogen's a little bit off. And the point of that is we rarely see nitrogen-nitrogen single bonds, and even nitrogen-nitrogen double bonds are unusual. All right. Now what I want to do is take a look at the silicon hydrogen and oxygen-oxygen bonds. So take a look at your chart there. Silicon hydrogen and oxygen-oxygen. And for those of you at home, I'm going to go back to the chart. So try to remember those. Oxygen-oxygen is in the second column, and silicon hydrogen is at the top of the third one. So first, look at the lengths of those bonds. Pretty similar length, right? Okay. Now compare the energies. Similar energy? Not at all. Okay. So the oxygen-oxygen single bond, similar to the nitrogen-nitrogen single bond, very weak. Not quite as weak as the nitrogen-nitrogen one, but the oxygen-oxygen one's pretty weak. When we have an oxygen-oxygen single bond, we call that a peroxide. So you probably heard of hydrogen peroxide. Might have it at home, usually comes in a brown bottle because it's light sensitive. And you put it on cuts to clean things. So it can be very reactive. Not so terribly reactive that it is dangerous for us to put on cuts. Some people actually will use it as a mouthwash. But what you have at home is only 3%. If it is used for cleaning pools, if it is used for, sometimes it's used in hair treatments, then it's usually more like 15% or 30%, much higher percentages, and then it becomes dangerous to work with. Any other peroxide is generally considered to be very reactive and dangerous. You don't want to have those. And you'll have, if you take organic chemistry, they'll have specific precautions to take so you don't form peroxides. You don't want to do that. And so, I'm going to use this to kind of come back to the idea of the energy of the bonds. So this is a weak bond. It does not have a lot of energy, but it's very reactive. The reactions that involve it tend to involve a lot of energy, forming a lot of energy. And that's because it doesn't take much to put in to break it apart, but then those molecules are going to go and form other molecules that are much more stable, and that will release energy. Okay. How many of you have had a biology class where you learned about ATP? Most of you, right? Okay, you probably had a biology professor that told you that ATP has that third phosphate, the T is tri, so the third phosphate will break off. And what happens when you break off that third phosphate? Oh, we don't remember. Maybe I don't have to worry about this, but they usually tell you it releases a lot of energy. Okay, does that sound familiar? So ATP is that energy molecule. You're not actually releasing energy. You have to put energy in to break that molecule, but it is a weak bond, much like this oxygen-oxygen bond is really weak. That phosphate then goes and combines with other molecules. The ADP combines with other molecules. And between the two of them, they're forming more stable molecules, and that's where the energy is released, okay? So forming bonds releases energy, breaking bonds requires energy, all right? This idea of ATP kind of gets you confused because you're thinking, oh, breaking that bond releases energy. Breaking the bond doesn't release the energy. It's the act of forming new bonds that releases the energy. Okay, so let's get back to the slide here. So what we've learned is that the strength and the length also depend on the specific atom. So if I'm comparing two atoms that are the same, carbon-carbon bonds, the longer the carbon-carbon bond, the weaker it is. The shorter the carbon-carbon bond, the stronger it is. But if I change all of what atoms I'm looking at, that's going to be very different. And then we already compared carbon-carbon and carbon-nitrogen for their double, triple bonds. So usually the value added, the additional bond order, is increasingly less energy, not less total energy, just the amount that we added. The total energy will always increase, just not by as much as the original bond. So usually it is a smaller value added, but this depends on the element. And nitrogen is our notable exception. Okay, so this was the calculation that I was telling you that I will test you over it, but it's going to be worth a small amount of points because it's not as important as the general ideas of how strong or long the bonds are. Okay, but we have these numbers. Some physical chemists have worked long and hard to determine these numbers for us, looking at lots of different chemical reactions to determine how long the bonds are and how much energy it takes to break them. And so what we can do is we can say, if I have a chemical reaction that involves these bonds that are in this table, I can approximate how much the energy of the reaction is by approximating or by calculating how much energy it takes to break the bonds and how much energy it takes to form the bonds. All right, so we have here methane. Now, did Dr. Fraley have you memorize some organic molecules like methane or no? Okay, so I'm seeing some nodding. So we should know methane has a carbon in the middle and hydrogens on the outside, and it is reacting with oxygen, which is one of our diatomic molecules. And what we see on top of that is it says bond breakage, and then it says 4Be C-H equals plus 1652 kJ. So what does that mean? The Be refers to the bond energy, And because there are 4 bonds, and so I've drawn methane here on the board here, we have 4 carbon-hydrogen bonds. Each of those breaks, so we're going to count the energy for each of those. And then we have a positive because we're breaking the bonds. Breaking bonds requires energy, so it's positive, okay? And then with the oxygen, each oxygen molecule only has 1 double bond, but there are 2 molecules, so we have to count it twice, okay? So that's why we have 2 for the oxygen, and then we just add those all up. When we do that, we end up with the atoms that are listed at the top. And then at the bottom, or I'm sorry, on the right, it is most towards the bottom, but it's on the right, we have the new molecules that we're forming in this reaction. So we have the carbon dioxide and we have water molecules. So remember with the carbon dioxide, we had 2 different numbers for the carbon oxygen double bond. So we're going to take the one for carbon dioxide, which was the 799. And then for the water molecules, we have 2 water molecules, but each of those water molecules has 2 oxygen hydrogen bonds. So we're going to count 4 total bonds there. So you'll notice in the calculation that's above that picture there, we have 4 oxygen hydrogen, and you'll also notice that each of those numbers is negative because we're forming the bonds, releasing the energy. All right, so you get the idea of what this picture is showing. Okay, important things to remember when you're doing this: stoichiometry matters. So it matters that we had 2 oxygens, it matters that we had 2 waters, but it's also important to remember that we're counting bonds, not molecules. So when you have something like the methane that has 4 bonds or the water that has 2 bonds, you have to count all the bonds that are in there, okay? So when we put all of these numbers together, we end up with the, by the orange arrow in the middle, we end up with the -818 kilojoules. Now this is just an approximation because everything that's on that chart is an average of lots and lots of different molecules. Okay, so in specific atoms, they might be a little different. And we saw how the carbon dioxide was a little different. Is this how reactions really happen? Do we really break apart the entire atom or the entire molecule and reform them? No, not really. But it is a good way to approximate the energy that we will see. All right, so I haven't said it enough. Breaking bonds is endothermic and therefore positive. It requires energy to break a bond, even an ATP triphosphate bond. Forming bonds is exothermic and releases energy, and therefore it is negative. Right, so we have the equation at the bottom. Now we've seen this delta H before. Delta means the difference. H is our enthalpy of reaction. So as long as we are not doing this in a high pressure situation, constant pressure, we have the energy of the reaction. And this is equal to, and then we've got the Greek letter sigma there. It looks like an E, but it's a sigma. What does that mean? Sum. Okay, so we have the sum of all of the broken bonds, which are positive, and the sum of all of the formed bonds, which are negative. And you may also notice there's this little circle up there. That means standard state. That's not real important to us. It just means this was done at room temperature and atmospheric pressure. So if you're doing this in a high pressure chamber at an extreme temperature, then all bets are on. But we're always going to do things at room temperature in, well, room temperature for our lab, which is not 25 degrees Celsius. It was about 15 degrees in there yesterday. If you had lab yesterday and you were cold, 15 degrees Celsius. That's 60 degrees. Simple reaction between hydrogen and fluorine, both diatomics, both have single bonds between them. And we're going to form hydrogen fluoride, also a single bond. So this keeps this nice and simple. If I were to look this up on a table of thermodynamic reactions, like we have in the back of our book, and we talked about them briefly in chapter 5, I would find that this reaction is negative 546 kilojoules per mole. So what that means is somebody actually did the experiment, reacted these together, and determined how much the temperature change was, and from that figured this number out. So this was experimentally derived. So we're going to see if we can come up with a pretty close number by doing our calculations. Why would we want to do that? Well, hydrogen fluoride is very corrosive. It's an acid, and you can't store it in glass because it will eat away at the glass. Okay. So if you've ever seen etched glass where like it's mostly clear, but there's like a frosting on it, what they do is they use hydrogen fluoride to do that, leave it on there for a couple of minutes and then wipe it off so it doesn't keep eating through there. So you might not want to do this chemical reaction. So we ask ourselves what bonds are broken. We have one each of the hydrogen and the fluorine bond. And we ask ourselves what bonds are formed. We have a hydrogen fluorine, but notice the stoichiometry. There are 2 molecules, so we have to count the bond twice. All right, now this information is going to be on the next slide, so if you're not quite caught up, it's still going to be on the next slide. I just have to advance to it. Look up the hydrogen bond on your chart. I have kind of a mini chart here on the screen, or you can use the paper that I gave you. And the fluorine bond, we're looking at the energy, not the length. The energy is the first column on your chart. And we should see that hydrogen is 432. What's the fluorine bond? 159. And the hydrogen fluorine bond. 565. So this is an incredibly stable single bond. Most of our single bonds are under 400. But the hydrogen fluorine one, really, really stable bond. Okay, so now we're going to plug those numbers into our calculation. We're going to add up all of the broken bonds, subtract off the broken bonds in order to determine what the energy is. So when I do this calculation, I come up with negative 539. If you don't have your calculator with you today, I recommend you do this at home. Make sure that as you calculate things, you come up with the same numbers. Now, is it the same number as the number we got from our table, our thermodynamics table? No. Is it close? Yeah. Okay, so it's a good approximation. All right, we have one more example here. This one is going to involve methane, which we've already looked at, and chlorine. Chlorine, like fluorine, is a diatomic with a single bond. And then we have chloroform, which has this structure here. So it's like methane, only the chlorines replace 3 of the hydrogens. So each of those carbon-chlorine bonds is a single bond. Now you could determine that using your Lewis dot structures, you know how to make. And then hydrochloric acid, HCl, is also a single bond. So calculate your broken bonds, calculate your formed bonds, or at least set it up. If you don't have a calculator, at least write down what would be the math you would do to figure this out. Generally, the best thing to do is assume that every bond on the reactant side is broken and every bond on the product side is formed. So once we go through this, I'll explain why I'm pointing that out. If you don't have your calculator, see if you can figure out just by ballparking it, which of these would be the correct answer. If you take the MCAT, I think they still don't let you use a calculator. So when you're doing multiple choice, the exact answer isn't the important thing. It's knowing what general range you're supposed to be. And I know not all of you are taking the MCAT. I'm just using that as an example. I'm going to give you about 30 more seconds to come up with an answer, and then we'll do a poll. All right, how many of you think it's A? That's good. That would be having everything be negative, which it's not. How many of you think it's B? Okay, how many of you think it's C? And how many of you think it's D? Oh, we got a bunch of chickens in this class. Only 4 of you responded. Good grief. Okay, the correct answer is B on this one. So definitely plug in those numbers so that you can have the confidence to respond. So notice that if I compare methane to chloroform, I have this one bond between the carbon and the hydrogen that I broke it and then I reformed it. And obviously when this chemical reaction would happen, that wouldn't occur and those numbers are going to wash out anyway. So if you notice things like that, it is legitimate to say, well, I'm just breaking these 3 and forming these 3 and I'm not doing anything with this. I don't recommend that because often what happens is people will remember not to count it on one side and then do count it on the other side and then the number is off. So show your work, because if you do something like that, I might take off a little bit of credit, but if you give me the wrong number and don't show me your work, you're just getting a 0. All right, any questions before you go?